Oh, yeah, thank you. Yes, so I will, okay, so the first part is about random directed graphs. So the problem here is fairly simple to explain. So suppose you have a graph which is directed. So it's a bunch of nodes connected by directed edges. Then we can represent this by a matrix, which is a table of numbers. And if there is a directed edge, we go to 1. If there's not 1, we go to 0. That's called the adjacency matrix, representing the graph structure. In addition, we can add weights to these links. So we denote that the weights by a real number. So each link has a certain real number. So that's a directed graph, and these graphs are interesting because they describe all kinds of complex systems. For example, here you have an example of an ecosystem, and every node would then be a certain species, and there exists a link between two species if one species feeds on the other. That's a system that can be represented by a directed graph. But there exist lots of examples. For example, there's the World Wide Web. It has about 2 million nodes. It's a directed graph. There are neural networks, which are directed graphs. There are also very large networks. There's social networks, etc. So diagonalizing these matrices is simply very hard because there are too many nodes. So we would like to have some theory to understand how network structure relates to the spectral properties of these graphs. So that's the general motivation. So then let me phrase the problem. So we look at the eigenvalues of the adjacency matrix A of a weighted directed graph. We order these eigenvalues from large to small. So lambda 1, we call it the leading eigenvalue. It's the eigenvalue with the largest real part. So since eigenvalues can be complex valued, we order them based on the real part. And this one we call the leading eigenvalue. So this will be our main quantity of interest, is the eigenvalue with the largest real part. And yes, the question is, what is the leading eigenvalue of a given directed graph? So why is this an interesting question? So of course, it's interesting by itself, interesting problem in itself, but it also allows us to understand complex dynamical systems, at least arguably the simplest example of a complex system, which is a linear system, a linear dynamical system, where the variables are coupled to the random graph or the network represented by this matrix A. I like this kind of system because it's the simplest example of a complex system in a certain sense. It's a linear system. If we don't understand the linear system, then how can we understand nonlinear systems? So it's a very nice, simple toy model to understand. So we can solve this explicitly since it's linear. And the solution is given in terms of the eigenvalues and the right and left eigenvectors of the matrix A. So it's a linear combination of the right eigenvectors in this case, with the coefficients that depend on time and the exponentials, and these are the eigenvalues that appear in the exponentials. So now in the asymptotic limit of large times, we see that if the real part of the leading eigenvalue is negative, then x converges to 0. We say that the system is stable because it converges back to the origin. On the other hand, if the real part is positive, then in the limit of large times, the norm diverges. And this means that the fixed point is unstable. So that's the interpretation we can give to the leading eigenvalue of this matrix for dynamical systems. So let me mention that this result here only works if A is diagonalizable, but the stability also works for non-diagonalizable matrices because you can do a Jordan decomposition. So the system stability, these conditions are valid irrespective of whether the matrix is diagonalizable or not. So which kind of results are known? So these are kind of classical results. So the first is for dense matrices, fully connected matrices. In this case, there is a seminal paper by May, which showed that the leading eigenvalue is proportional to the square root of the system size. And then this is for non-directed random graphs as well. This is a well-studied problem. In this case, the leading eigenvalue is proportional to the square root of the maximum degree of the graph. So these two results imply the following. If the graph becomes large, then this lambda1 diverges. But as well for a non-directed random graph, lambda1 will diverge because the maximum degree will diverge. So people speak here of the trade-off between complexity and stability, because if a system gets very large, lambda1 will inevitably diverge, which means the system will become unstable. It's called complexity stability trade-off. So now let's look at directed systems. What can we say about directed graphs? So let me define the system, so we will look at a random model for the network. So for the adjacency matrix, we consider a random graph, but with a prescribed distribution of indegrees and outdegrees. So indegrees and outdegrees can have correlations, but we are given a certain prescribed distribution of in and outdegrees. So this model works as follows. So you have n nodes. Each node, independently, you draw an indegree and outdegree from this distribution, and then you randomly connect these nodes given the indegrees and outdegrees. So that's the model for the random graph. How about the weights? So the Jij, well, we choose them independent and identically from a certain distribution P of J. And that's the model that we will study. That's the model we will consider the spectral, the eigenvalues of this model. So let me show you how this type of graphs look like. This is an example for Poisson distributed degrees. It's a graph of size 100. The mean degree is 1.5. And then you get, if you plot this, you get something of the following form. So these directed graphs have interesting topological properties. So there is the so-called bow tie diagram, which is topological characterization of the structure of directed graphs. And it's a bow tie because it really looks like a bow tie. So the center of this representation is a strongly connected component, or the largest strongly connected component. And this is a graph where each node can reach each other node. That's called strongly connected. And then we have here the in component. These are all nodes that can reach a strongly connected component. There's also the out component. It's all nodes that can be reached from the strongly connected component. So the strongly connected component is quite important for the spectral properties of the graph. So that's why I mentioned this. So as we will see here. So as well, there are some disconnected cycles. They will as well turn out to be important, you will see eventually. So this is just an example. So this is a simple graph, and in this case, a strongly connected component, or the largest strongly connected component, consists of 4 nodes. And we will, so this number is important, is the fraction of nodes that belong to the largest strongly connected component. This number will be important. So, okay, so I recall that SSC is the fraction of nodes belonging to the largest strongly connected component. So let us look at the case where this is positive. So this means that the graph has a giant strongly connected component. So in this case, we can characterize all this not all, but many important spectral properties of the graph, as we will see. So this is an example of one matrix. The blue dots are all the eigenvalues of this matrix. So in the center, there's a delta peak. And this delta peak, the weight of this delta peak is given by the fraction of nodes that do not belong to the largest strongly connected component. Yeah, so here you see why this must be greater than 0. If this is 0, then the delta peak will be 1, and everything is concentrated in the center. So then there is this circle. You see that all eigenvalues are confined in a circle. So we can characterize analytically the radius of the circle. It's given by the mean outdegree times rho plus 1. Rho, as we will see, is terms the correlations between in and outdegrees. And then the expected value of j to the power of 2. J is represents the weights of the links. And then there is one lonely isolated eigenvalue outlier, which actually will be important because the largest one is often the outlier. And this one is given by C times rho plus 1 times the average of the weights J. So what is C? Well, C is just the mean out and indegree. And rho depends on the correlations between in and out degrees. So this picture captures almost everything, almost all properties of the spectrum, at least when we're interested in the largest, the leading eigenvalue. Then you see here, we find all properties. And this is really general because this is conjecture to hold generally for graphs with a given distribution of in and out degrees and with weights which are randomly drawn from this from a distribution. So I would like to briefly maybe explain where these results come from, just to give you an idea how we derive these results. So the key idea to obtain these results was somehow to look at the eigenvectors instead of the eigenvalues. That was somehow the key insight. So, and we would define the distribution of entries Ri. So Ri is the right eigenvector associated with the leading eigenvalue. And P of R is the distribution of these entries of the leading right eigenvector. Then there is Q of R, which is strongly related to P of R. It's again a distribution of eigenvector entries, but we sample them differently. So P of R, we sample uniformly and randomly nodes. In Q of R, we randomly sample edges, and we look at the endpoint of one of these edges. So that gives us Q of R. And the key point is that we can derive a recursion relations in these distributions. So this is probably the most equation-heavy slide, but I hope I can just explain the idea. So here we have the distribution of entries of this right eigenvector, which is expressed in terms of Q of R, of its neighbors, and then we find a closed set of equations in this Q. So these equations can be solved, and it gives us a distribution of entries of the right eigenvector associated with a given eigenvalue lambda. So if you have a given eigenvalue lambda, this will give you the distribution of entries of the right eigenvector associated with this eigenvalue. And now the somewhat amazing thing is that we can use these equations to find the eigenvalues, which a priori is maybe not so obvious. And we can do that because we will look at the solution which is normalizable. So if for all values of lambda for which a normalizable solution exists and gives us proper eigenvalues, or gives us spectral properties. I will show you how this works. So let's first look at the first moment of these equations. So this is, if we determine the first moment, we find a self-consistent equation in the first moment, which is this equation. And this, to have a non-trivial solution, we need that this is equal to 1. Otherwise, the mean must be 0 or infinitely large. So this must be 1 to have a non-trivial solution. And this gives us the outlier. So that's how we find the outlier of the network. And how do we find the boundary of the spectrum? Well, you see, we can as well put the mean to 0. Oh, yeah, please, yes. Oh, of course.
Just square in the integration measure, then b squared r. Sorry, that's maybe not a very naive question. Where's b squared?
Yeah, that's not a naive, that's a very good question. So, no, you can replace it by any exponent. It doesn't have to be square. Yeah.
Okay.
So, yeah, that's as long as it's not a delta peak at 0, or the entries don't diverge. So in fact, it doesn't have to be a square. As long as you can actually find regions where this actually is divergent, but then you find a finite solution for, let's say, the modulus of r to the power of 1.5, and that still gives sensible results. Yeah.
You're answering. I'm not asking about the r square on the right hand side, the one on the left side, or the one on what would be.
Oh, that one. Oh no. Okay. I was then overthinking the question probably. No, that's because r can be complex values. So there's it represents the imaginary and the real parts of r.
Thank you.
Oh, thank you. Yeah, so but the nice thing is this gives us exactly the outlier when but you see, we can also put r to 0, the mean value to 0. And so if you put the mean value to 0, what we do is we look at the next moment, which is the modulus of r to the power of 2, and we request that this has a sensible solution. And for this, we need the prefactors as well, 1. And this gives nicely the circle that we needed. So this gives the eigenvalues at the boundary. So that's, I hope, at least gives you more or less the idea of the derivation. So this gives us nicely all these properties of the spectra of the random directed graph. So what's now the leading eigenvalue? Well, the leading eigenvalue is simply the maximum between the outlier and the maximum value of the circle, so the radius of the circle. If this quantity is greater than 1, so why is that necessary? Well, that determines the fraction of nodes in the largest strongly connected component. So if that's a percolation transition of a strongly connected component of the graph. So if this is smaller than 1, lambda 1 would be 0, according to this theory. So what is remarkable about this is that, I mean, it took me actually some time to realize this, but in a sense, it's really remarkable. The leading eigenvalue is finite, because we have seen in non-directed graphs, the leading eigenvalue scales as a maximal degree, but in directed graphs, it's finite. So even if the norm of the matrix diverges, you still have a leading eigenvalue which is finite, which is non-trivial and somewhat remarkable. Another thing, which is, I think, remarkable, it's really universal. So you see these formulas work for arbitrary prescribed distributions of in and out degrees. They work for which is that in this derivation, we ignore small cycles. So this is based on the cavity method, which ignores the existence of small cycles in the graph. And for the global spectral properties, this does not matter. But if you look at the leading eigenvalue, since this is an extreme event, the small cycles can matter. And this is what I want to briefly discuss now. So what will small cycles do? If you think about it, you realize that they can create also outlier eigenvalues, but they won't be deterministic, they will be stochastic. So you may occasionally have a random matrix realization with a stochastic outlier eigenvalue. And how is that possible? Well, the argument of the existence of those stochastic outlier eigenvalues is fairly simple. It goes as follows. Suppose, a network will always have a probability to have disconnected cycles of this form. So these are strongly connected components disconnected from the largest strongly connected component. And these cycles, you can compute the eigenvalues of those. So they lie on a circle with radius gamma. Hence, if the weights of these circles are large enough, you will get a stochastic outlier eigenvalue. So this probability is small, but non-zero. So they must exist in certain random realizations. So the more correct picture is the following. This value lambda star we determined before, but there is this glitch that if there are strong enough cycles in a network, then they will generate a larger eigenvalue. So there's this, which the cycles we cannot account with the cavity methods, so they are beyond reach. They're small cycles, and long cycles are fine, but these are small cycles, triangles, etc. Cannot account for them. But there's one case which is exactly solvable, which is the case where all weights are equal to 1, because in that case we can determine, we know that the cycles cannot be larger than 1, radius 1, and then we can determine their contribution. So above the percolation transition, the leading eigenvalue is the outlier, and there's no stochastic outliers. Below the percolation transition, on the other hand, the leading eigenvalue is the sum of two delta peaks. One is the probability that there exists no cycle, then the eigenvalue is just 0, everything is located in the origin. The other one is the probability that there exists at least one cycle, that's P plus, and that then compute it using some probabilistic arguments, so you can determine that. So to give you some illustration of this, so here we are below the percolation transition. And then if you diagonalize a couple of matrices, you see that this circle, this disk of eigenvalues does not exist. Instead, you have eigenvalues which are located on circles. Above the percolation transition, you have this continuous spectrum, at least in the infinite limit. This continuous spectrum in the disk exists. And we have these outliers, which are lonely outliers outside the disk. So we can, so this has exactly radius 1, because these are the cycles. This is C is 2, this is the outlier located at 2, and this is exactly square root of 2, because mean degree 2. So we can compare this a bit more quantitatively with numerics. So here we plot the leading eigenvalue as a function of rho, which quantifies the correlations between in and out degrees. So the rho is negative. This means that in and out degrees are anti-correlated in this ensemble. The percolation transition is this dashed line. So left, you have a graph without strongly connected component, or at least without a strong without a giant strongly connected component. To the right, we have a giant strongly connected component. So this is a percolation transition. And we can compare the theory. So here, this is the outlier. The theory says 0 plus 1. This is, you see, this is the regime where the existence of the cycles matters. So we have this formula for the probability that there exists a cycle that works as well. But as well, note the large fluctuations. So here you have as well large fluctuations because it's the existence of such a cycle that determines the leading eigenvalue. So this is universal, so you can take another degree distribution and it should give the same result. So that's what we have done. And we can as well look at the second leading eigenvalue. And this should match here with this value of the disk, which as well works. So that's somehow summarize this part. I think, oh yeah, no, there's one more thing I want to say, which is about the phase diagram. So let's look at let's use this to determine the stability of a dynamical system defined on a random directed graph. So for this, to say something, so here, what matters is whether the eigenvalue is negative or positive. So we need to be able to have negative eigenvalues. We do this through a simple trick. What we do is we subtract a matrix proportional to the identity matrix, which has this value d. So this is a constant shift of all eigenvalues to the left. And this allows us to get a phase diagram for the stability of a linear system on a directed graph, a random directed graph. And as we have seen, this should be universal. So you can get this universal phase diagram, which is shown here. So on the y-axis, we have the connectivity of the network. So it's the mean outdegree times, this is basically the branching ratio of the network. On the x-axis, we have the weights. This determines the weights of the network. So we have the variance of the weights divided by the mean. And then this red line separates the gapped region where there's no outlier from the gapless region. The other way around, the gapped where there is an outlier from the gapless region without an outlier. And the dashed line here is what separates the unstable region from the stable region. So you see this, how you can read this is, for instance, if you decrease the connectivity or you increase the connectivity, then you can become unstable. If you increase the variance of the couplings, you also can get unstable. That's how you can read this phase diagram. Yes, so that should be determined by the d, the value of d that we've chosen. So here we took the mean value of j divided by d 1/3, and you mean when the gapped becomes the gapless? Yes. Yeah, I think this must, no, they must be related to this. Yes, exactly. Oh, yeah, that is actually, this is this formula here of 0 plus 1. Okay, this formula, yes. And you see as well, the outlier is independent of the fluctuations of J. That's why here, this is flat. So if here you change the fluctuations in the couplings, you don't affect stability. That's because the leading eigenvalue is an outlier. So, and yes, you can change this d, this little d, and then you can change that. All right, so we can as well look at the properties of the eigenvector, the right eigenvector. And one interesting property is the inverse participation ratio, which is one way to quantify how localized the right eigenvector is. It's not the only way, but it's one measure of localization. And you see if you're delocalized, it should be 1. If you're localized, it's infinitely large. That separates localization from delocalization. And interestingly, we can as well derive analytical results for this inverse participation ratio for random directed graphs. So there are, in fact, 3 inverse participation ratios. There is the outlier, there is the boundary, and there is the boundary when you're real. So they're different. So the boundary you're not real, the boundary you're real, gives different values. And everything inside the spectrum is inaccessible with our methods, so that we can't say anything about. We only say something about the boundaries. So I will spare you the formulas, but I just give you the phase diagram that we find. So the delocalized region means here inverse participation ratio finite. Localized means inverse participation ratio infinitely large. So we've done this for rho 0, so there's no correlations between in and out degrees. And we also well need that the 4th moment of the out degree is finite. If this one diverges, then we as well have a localization. So we look here where the 4th moment is finite. So we don't look at localization due to degree fluctuations. So what we can say here is, so again, this is a universal phase diagram. And you see that what's interesting is that if you decrease the mean degree, so the localization is determined by the mean degree in this case, the degree fluctuations do not matter. That's quite surprising. Just the mean degree, and if you decrease the mean degree, at some point you get localized. So degree fluctuations are irrelevant for localization in this model, except if the moment becomes, if the 4th moment diverges. But if the 4th moment is finite, localization is independent of degree fluctuations, which is, I think, maybe not so obvious, at least not to me, isn't me. But localization is affected by the variance in the weights. So sigma is the variance of the J, or it's the standard deviation better. Mu is the mean value of the J. Then you see if you increase the variance, at some point you get localized. So the localization is here governed by the variance in the weights. We can find a formula for these different lines. So this is the this determines whether there's a gap, an outlier or not. This is the formula for the localization of the eigenvectors at the boundary of the spectrum. So you see it's determined by the 4th moment of the weights, J. And finally, the outlier, the eigenvalue outlier, is localized. The localization is determined by this condition. And you see that this is, I guess, this is not obvious to me neither, but it seems that eigenvectors at the boundary localize before the eigenvectors at before the eigenvalue outlier, because this line lies below the short line. CS1 here denotes percolation. So we stop at 1 because below the graph does not have a strong event component. That's why we plot it from above 1. That's so this so this closes, I think, everything I can say about directed graphs. So to summarize, so one interesting finding is that for non-directed graphs, we have that the leading eigenvalue is proportional to the square root of the maximal degree. For directed graphs, the leading eigenvalue is proportional to the mean outdegree. So if for random graph, this would mean that the leading eigenvalue is finite in the directed case. It diverges in the non-directed case. At least for an infinitely large, let's say, Erdős-Rényi graph, this would be the case. Of course, if you look at a regular graph with finite degrees, then everything is finite. But for an Erdős-Rényi graph, it diverges for directed graphs, and it's finite for directed graphs, it diverges for non-directed graphs. But this raises an interesting question, which is which other network structures have a finite leading eigenvalue? Because we have looked at directed case. What happens if the weights become non-directed? So this brings me to random non-directed graphs. So here we have looked at the following possibilities. So we have, so this is oriented, which is that directed. Basically, if you have a link in one direction, there is no link in the other direction. But how about antagonistic? Antagonistic means if in one direction the weight is positive and the other direction is negative. So it's also called sign antisymmetric. The values can be different. So it's not the same as antisymmetric because the values of the weights can be different. It just means that in one direction it's positive and the other direction is negative. And then we have a mixture ensemble, which means that you have some links which are predator-prey. This is all called, in ecology, people call it predator-prey interactions. But you as well have plus plus and minus minus, which are sign symmetric interactions. Minus minus in ecology is called competitive, plus plus is called mutualistic. So this is the result that we obtained. So we plotted the mean value of the leading eigenvalue as a function of n, and we compared the antagonistic, which is a sign antisymmetric case, with the mixture case. So mixture means that you can have sign symmetric interactions. They don't all have to be, but a finite fraction of them has to be. And somewhat remarkable is that the antagonistic case, you see it, the leading eigenvalue is finite. In the mixture case, it diverges. So the antagonistic case shares with the directed case that the leading eigenvalue is finite. On the other hand, the mixture case shares with the symmetric case that the leading eigenvalue diverges. So that was when we found this, we were really surprised because we hadn't expected that. We were just out of curiosity looking at this ensemble. So then we looked at this a bit more detail. So here is the full spectrum of this antagonistic Erdős-Rényi ensemble. So this is for increasing sizes. For a 10 by 10 matrix, of course, we have diagonalized tons of matrices so these is a collection of 1,000 matrices, something like this. On the other hand, for 10,000, this is one matrix that has been diagonalized. The solid line follows from the theory, and this is the boundary predicted in the infinite size limit. And for this, there exists a theory which actually was developed by Tim Rogers and Izaak Perez-Castillo, which determines the spectral distribution of sparse matrices. And so it's a different cavity. It's also a cavity method, but a different one that I explained to you before for random directed graphs. And this one, so we use this theory, but we found the criterion for this boundary and we obtained that. The red line here is the elliptic ensemble, the equivalent dense ensemble. So how about the mixture case? So why does the leading eigenvalue diverges in this case? Well, if you plot the spectra, you can see what's going on. So what happens is that here you develop tails on the wheel axis. So whereas in the previous case, see it crosses the wheel axis orthogonally. Here it develops long tails on the wheel axis. And this we find both in the theory as in the direct diagonalization. So in both cases, you can confirm that you have these infinite tails on the wheel axis. And that's the difference between this antagonistic and this mixture Addy-Swing ensemble. How much time do I have?
5 minutes.
I think then I might stop here because there's a different topic. So I had something on this random economies, but I think I need more than 5 minutes. So maybe I just stop here. If,
time for questions.
yeah, maybe. Yeah, I will, because it's a new topic, I will just stop here. And maybe I will just go to the last slide. I mean, since it's a new topic, I can perfectly well.
Curious about what's this about. just a minute, I guess, to understand. Yeah.
Sorry, what?
Maybe just a minute to see.
Oh yeah.
This section about.
Oh yeah. I will. Okay. Okay. Then I apologize. I might go very quickly through this, but there was this model by Moran-Bouchot on stability of random economy, which yeah, here the network, basically you have firms and they're selling products to each other, and the network tells which products each firm buys from each other firm. And then they have a model that determines the firm sizes of these firms in a competitive equilibrium. That's what they call. So they find, so the model is, I'm not, this is out of my let's say expertise, but I can understand the model. It's based on a balance equation for profit. So this is the profit of a firm is its revenue minus expenses, basically. So P is prices of the goods, pi is the total number of goods produced, and Q is just the number of goods firm I buys from firm J. And then you see that this is basically this is how much money comes in and how much money goes out. So these are too many variables in this model. So I will just, because of time constraint, I just skip, but they make enough assumptions until that they get a condition, which is that the real part of the, in this case, the minimal eigenvalue is positive. So you can map the problem of spectra on the problem of the stability in what they call competitive equilibrium, because the profit must be zero in this model that they call as competitive equilibrium. And the condition is based on the positivity of the prices. And then they have this numerical diagram. This is from the Moran-Bouchot paper. They have this numerical solution. So the point is that you can almost immediately apply our results to this model to obtain the analytical expressions. And yeah, I can just show you. So this is this was, oh yeah, so yes, eventually you get this again, the stability and instability, very similar to what we have seen before. But this is so one is the outlier, the other one is the continuous spectrum. So there's a line where stability is determined by the outlier and here's by the continuous spectrum. And then you can find, using the theory, you find for this line simple formula. So that's basically the remaining story. And yeah, I think that summarizes.
Thank you for the
Oh, thank you very much for your attention.
So we have room for another hour. And so if you have questions, you can ask, we can ask if you're still available. We can
Yeah,
ask
as much
and,
as you
we have
like.
some pizza and some drinks.
Oh, okay. That's good.
Yeah, so I don't know if we have questions from the audience. I will have a
Yeah.
question.
Yeah.
So in the directed case, you have this row, right? Which is the correlation between the in degree and the out degree.
Oh, yeah. Yeah, absolutely.
So and I'm trying to make sense of this finite largest eigenvalue.
Sure.
Yeah, difference between direct and non-direct graph, which is kind of surprising.
Here, yeah.
So what's surprising is to me, and I think the sample on mutualistic and mixture models started to kind of shed light on this result, I guess. So there is something that happens in indirect graphs that makes the largest eigenvalues diverge, which doesn't happen in directed graphs.
Yes,
right?
yes. Yeah, so
so what I don't understand is raw doesn't allow you to, in any case, to get to divergence. So
no.
Okay, that's the question.
Yeah, the raw doesn't allow you. So but we have an understanding. We actually explained this in the paper at the end of the paper with Andrea and Chiara. We have, as well in this paper, we explained that we have an intuitive understanding why the leading eigenvalue is finite. I mean, it took us a while to get it, but we have it. And that's because if you look at a directed tree graph, because a cavity method is a local method, it looked at the tree structure, basically, right? And a bit infinite tree structure. And if you look at a finite directed tree, all eigenvalues are 0, which was well known, and this was clearly understood by us, and we knew this is why the leading eigenvalue is finite. But what we didn't know is, now if you look at a finite, if you look at a tree which is antagonistic, so antagonistic, a tree which predator-prey interactions. Yes, sorry, there's some jargon, which is the fault of the ecologists.
So antagonistic.
Yeah, antagonistic. Yeah, so if you look at an antagonistic predator-prey tree, what happens is that all eigenvalues lie on the imaginary axis. And yeah, and the point is that the loops, the cycles, they're long, so they manage to spread out the spectrum, but they can't make it infinitely large. So what happens? And yeah, that's the distinction between these models and the other models.
Thank you.
Yeah.
So it sounds like the mutualistic part is the one that.
Yeah, the row doesn't matter because it doesn't. You still have locally directed tree. That's why row doesn't matter. So yeah, the row changes the properties of the degrees, but it doesn't change the fact that it's a directed graph. It's something, yeah.
Thank you. Any other question?
On your degree,
Yeah.
you won't diverge, right?
Sorry, if
If you bound your degree to some number, you will not diverge at all, or
it depends. So bounding degrees is not sufficient. You have to bound the norm. So if you have bound degrees, but a distribution of weights which is unbounded, then it still will diverge. Yeah, but you have to bound the norm, because if the norm is bounded, then definitely it will be finite, because the leading eigenvalue must be smaller than the norm of the matrix, and everything has to be finite. So the degrees and the weights have to be finite for that. And yeah, then of course there's no discussion that things finite.
What's the why you want to look at the graph with the infinite side and the vertical side and what's the
yes, so there's well, there's various reasons, of course. One is that's the case where we can do, of course, theoretically, that's a case where we can solve things, so finite, and we can't say practically anything. But then there's another, for instance, there is this argument by May, which says that if a system becomes, if it diverges, it means that if the system is large enough, then eventually it will become unstable. There is this, these systems have kind of a trade-off between size and stability. It's called stability complexity trade-off.